Three-dimensional coordinate systems, Level 1. Calculus 3 is a course that uses all the concepts learned from Calculus 1 and extends it to the study of functions with two or more variables. In a nutshell, Calculus 3 is Calculus 1 in 3 dimensions. Nothing more, nothing less. With that said, this class will challenge your spatial visualization skills and push them to the limit. Before we dive in, we need to start thinking three-dimensionally and be familiar with a three-dimensional coordinate system. We first need to remember the basics of number lines. Back in Algebra 1, and perhaps even before that, you learned that a number line is formed when a numerical value is assigned to each point on a line. For example, the following line represents a number line, and point A is located at -1. Likewise, point B is located at 1.5, or written another way as 1.5. Notice that number lines are useful to describe the location of a point relative to the origin, which is usually assigned a value of 0. In other words, a number line can be viewed as a coordinate system, specifically a one-dimensional coordinate system, consisting of all the points on a straight line. Notice that this line is broken into two regions, or halves. The first half contains positive numbers, and the second half contains negative numbers. And for the most part, you can only move along the line, either infinitely to the left or infinitely to the right. In this sense, a one-dimensional coordinate system is equivalent to a number line, where every real number, whether rational or irrational, has a unique location or position on the line. Conversely, every point on the line can be interpreted as a number in an ordered continuum that includes the real numbers. We can mathematically denote this one-dimensional space that includes the set of all real numbers as follows, using the real number symbol. Now, if we take this number line and introduce an additional number line that is perpendicular to this number line, we obtain the modern coordinate system, also known as the Cartesian coordinate system, or the rectangular coordinate system. A two-dimensional coordinate system specifies each point uniquely in a plane, also known as the xy plane, as opposed to a one-dimensional coordinate system, which specifies each point in a straight line. As a result, a point on a two-dimensional coordinate system is described by a pair of numerical coordinates, also known as an ordered pair. Each coordinate in the ordered pair describes the location of the point along each number line, which are commonly known as coordinate axes. The value along the x-axis, also known as the abscissa, is called the x-coordinate of the ordered pair and is denoted first when describing a point on the plane. Likewise, the value along the y-axis, also known as the ordinate, is called the y-coordinate and is denoted second when describing a point. Together, the x and y coordinate form an ordered pair. Notice that a point is measured relative to a common center, where the two number lines intersect. This common point of intersection is called the origin, and is usually labeled by using the letter O. The ordered pair that describes this point is written as follows, 0, 0. As an example, the following 4 points can be described as follows. Point A is located at 2, 2. Point B is located at -1 and 1. Point C is located at -2 and -3. And point D is located at 4, -3. As you can see, each point forms a rectangle when applying their position, hence the rectangular coordinate system. Also notice that a two-dimensional coordinate system is broken up into 4 regions, also known as quadrants. They are usually labeled as follows: Quadrant 1, Quadrant 2, Quadrant 3, and Quadrant 4. In addition, the sign for each coordinate of an ordered pair is dependent on which quadrant the point is located. If the point is located in Quadrant 1, both the x and y coordinate will be positive. In Quadrant 2, the x coordinate will be negative, and the y coordinate will be positive. In Quadrant 3, both the x and the y coordinate will be negative. And finally, in Quadrant 4, the x coordinate will be positive, and the y coordinate will be negative. In a two-dimensional coordinate system, you are free to move along two lines, infinitely to the left, infinitely to the right, infinitely up, and infinitely down, as opposed to just one line, like that in a one-dimensional coordinate system. Mathematically, we can define all the points in a two-dimensional coordinate system by the Cartesian product r times r, or r squared, where r squared represents the xy plane, and it consists of all the ordered pairs where the values of x and y are elements of the real numbers. Let's move along and talk about the three-dimensional coordinate system, also known as the three-dimensional rectangular coordinate system. If we take the two-dimensional Cartesian axis and add an additional number line perpendicular to both axes, we obtain a three-dimensional coordinate system. The three-dimensional coordinate system contains 3 coordinate axes that intersect at a common point, also called the origin. These include the x-axis, y-axis, and z-axis. For the most part, the x and y-axis are horizontal lines, and the z-axis is a vertical line. Just like the previous coordinate systems, each axis contains positive values and negative values. On the x-axis, the positive values are located here, and the negative values are located on the opposite direction. On the y-axis, the positive values are located here, and the negative values in the opposite direction. And finally, on the z-axis, the positive values are located here, and negative values in the opposite direction. A way for you to remember where the direction of the z-axis is located is by using the right-hand rule. If you curl the fingers of your right hand around the z-axis counterclockwise from the positive x-axis to the positive y-axis, then your thumb points towards the positive direction of the z-axis. In addition, the 3 coordinate axes also determine 3 coordinate planes. The xy plane is a plane that contains the x and y axis. The yz plane contains the y and z axis, and the xz plane contains the x and z axis. Together, the 3 coordinate planes divide space into 8 regions called octants. This is analogous to the quadrants of a 2-dimensional coordinate system. In this case, a 3-dimensional coordinate system divides space into octants. The first octant is determined by the positive axis. If you're having a hard time visualizing this, just look at any bottom corner of a room. That's essentially a visual representation of the first octant. The wall on your right is a YZ plane. The wall on your left is a XZ plane, and the floor is a XY plane. In the same manner, there are 7 other rooms, 3 more on top and 4 more on the bottom. If you imagine this 3-dimensional coordinate system representing a 2-story building, there will be 4 rooms on top and 4 rooms on the bottom, each room sharing a common corner called the origin. In a 3-dimensional coordinate system, a point is located in space, as opposed to a 2-dimensional system where a point is located on a plane, and a 1-dimensional system where a point is located on a line. With that said, we represent a point by an ordered triple, x, y, z, of real numbers, and we call the numbers the x, y, and z coordinates of the point. In order to locate a point in space, we first start at the origin and move along the x-axis to locate the first coordinate, then move parallel to the y-axis for the second coordinate, and then parallel to the z-axis to locate the last coordinate. The reason why this coordinate system is called a rectangular coordinate system because points in space determine rectangular boxes. For example, the coordinate 4, 5, 3 is plotted as follows. We first move along the x-axis, 4 units in the positive direction. Then we move 5 units parallel to the y-axis in the positive direction, and then move parallel along the z-axis, also in the positive direction. Now at first, it's a little hard to see where the point is located, so we need to draw a corresponding box so we can get a better perspective and visualize this 3-dimensional plot on a 2-dimensional sheet of paper. The way we draw the box is actually pretty easy. All we need to do is draw 3 additional lines with the same length for each coordinate. So here we draw 2 lines parallel to the first coordinate that starts from the point 0, 5, 0 and ends at 4, 5, 0. Another one that starts from 0, 5, 3 and ends at 4, 5, 3. And lastly, one that starts from 0, 0, 3 and ends at 4, 0, 3. Then we draw lines parallel to the y coordinate, 1 for the bottom and 2 for the top of the box. Then we do the same for the z coordinate. We draw lines parallel to connect the bottom and the top of the box. In the same way, the following points will be plotted as follows. Point B will be located at 4, -6, and 6. Point C will be located at -3, -3, and 2. Point D will be located at -6, 3, and 4. Point E will be located at 4, 5, and -5. Point F will be located at 4, -6, -5. Point G will be located at -3, -3, -2. And point H will be located at -6, 3, -4. This is how the points will look like in a sheet of paper. Let's actually plot these points using a 3D plotter. Point A will look like this. Point B. Point C. Point D. Point E. Point F. Point G. And finally, point H. So we grab this Cartesian plane and move it around like this. We see that we have 8 distinct points, 4 of them on top of the XY plane, and 4 of them on the bottom of the XY plane. 1 for each octant. So it's really hard to see this by just using a 2-dimensional sheet of paper. But by using technology, we can actually see a better representation of how these points look like in 3-dimensional space. Just like the quadrants of a 2-dimensional coordinate system determines the sign of each coordinate, so does each octant. On the first octant, all 3 coordinates are positive. In the second octant, the x-axis is negative, and both the y and z axes are positive. In the third octant, both x and y are negative, and z is positive. In the fourth octant, both x and z are positive, and y is negative. In the fifth octant, both x and y are positive, and z is negative. In the sixth octant, x and z are negative, and y is positive. In the seventh octant, all 3 are negative. And finally, in the 8th octant, x is positive, and both y and z are negative. In a 3-dimensional coordinate system, you are free to move along 3 lines: infinitely to the west, infinitely to the east, infinitely north, infinitely south, infinitely up, and infinitely down. Mathematically, we can define all the points in a 3-dimensional coordinate system by the Cartesian product r times r times r, or r cubed, where r cubed, in this case 3D space, consists of all the ordered triples, where the values of x, y, and z are elements of the real numbers. Alright, make sure you're comfortable with this new 3-dimensional coordinate system. It's going to be key in understanding the rest of Calculus 3. In our next video, we will focus on graphing equations using this new coordinate system. Three-dimensional coordinate systems, Level 2. In the previous video, we reviewed the basics of 1-dimensional, 2-dimensional, and 3-dimensional coordinate systems. In this video, we will begin representing basic equations in 3-dimensional space. Before we dive in with equations, we need to be able to draw a 3-dimensional coordinate system and be able to identify and navigate through all its parts without getting lost. Let's first start with a traditional 2-dimensional Cartesian coordinate system. Recall that this coordinate system is formed by 2 axes, the x-axis and the y-axis, which are perpendicular to each other. In addition, this coordinate system is divided into 4 quadrants. The first quadrant is located here. Then we move counterclockwise to label the second, third, and fourth quadrant. Recall that each quadrant determines the signs on the x and y coordinate of a point. You can view the previous video with a more in-depth look on 2-dimensional coordinate systems. For now, I want you to keep in mind that a 2-dimensional coordinate system represents a plane. Now, when we draw a 3-dimensional coordinate system, we usually draw the standard placement of the axis, meaning we only show the positive axis for each variable, and we extend the lines for each axis when needed. So we first draw the positive z and y axis as follows. Then we extend the x-axis from the common point of intersection of the z and y-axis as follows. This is the standard position of a 3-dimensional coordinate system. Keep in mind that we will tend to extend the lines for each axis when needed. Also, keep in mind that all the physical drawings you make are done in a 2-dimensional sheet of paper. This means that you will have to use your spatial visualization skills to see most of these 3-dimensional graphs. But in these videos, I will create actual 3-dimensional images so you can start getting an intuition of how these graphs are truly represented. Let's take a look at our 2-dimensional coordinate system. It turns out that this coordinate system represents the xy coordinate plane in a 3-dimensional coordinate system, as shown on the right. If you view the plane from above, it's actually turned a little over 90 degrees clockwise. This means that the first quadrant is located here, the second quadrant here, the third quadrant in the back, and the fourth quadrant is located here. You really need to wrap your head around this and be able to view the xy plane in a 3-dimensional system. This way, you can translate all of your understanding of a 2-dimensional coordinate system into the xy plane of a 3-dimensional coordinate system. In addition, keep in mind that there are 2 other planes, the yz plane and xz plane. If you understand how graphs behave in the xy plane, you will easily understand how graphs behave in the yz and xz plane. It's pretty much the same concept. Alright, now let's actually start graphing equations. Recall from your studies of algebra that a graph in two-dimensional analytical geometry, in other words, in the Cartesian coordinate plane, involving the variables x and y, is represented by a curve in r squared. For example, the equation y equals 3 represents the following set, which is a set of all points, also known as ordered pairs, in r squared whose y-coordinate is 3. This means that this equation contains all the points whose coordinate is x3. The way we represent this is by plotting all the points in the xy plane, or in this case, r squared, whose y-coordinate is 3. Doing that, we would obtain the following points. Notice that every single point has 3 as its y-coordinate. Now, this set of ordered pairs is in theory infinite, so instead of plotting all the possible points, we usually represent all these infinite points by connecting them with a curve, as follows. In this case, we have a horizontal straight curve connecting all the points that are generated by the given equation. In addition, this line is also parallel to the x-axis and perpendicular to the y-axis. In the same manner, the equation x equals 3 represents the following set, which is the set of all points whose x-coordinate is 3. This means that this equation contains all the points whose coordinate is 3y. The way we represent this is by plotting all the points in the xy plane whose x-coordinate is 3. Doing that, we would obtain the following points. Notice that every single point has 3 as its x-coordinate. Once again, we usually represent all these infinite points by connecting them with a curve, as follows. In this case, we have a vertical straight curve connecting all the points that are generated by the given equation. In addition, this line is also parallel to the y-axis and perpendicular to the x-axis. Notice that when you have an equation with a single variable, such as y equals 3 or x equals 3, the second variable is free to take any value, since there were no restrictions on that variable. This idea will be very important when we start graphing equations in a three-dimensional coordinate system. So let's go ahead and graph the equation y equals 3 in r cubed. Notice that from this point on, it's key to specify what coordinate system we are referring to. Is it r squared or r cubed? Since this will determine how many variables we're going to deal with, and ultimately determine the final graph of the equation. In this case, we are graphing y equals 3 in r cubed. This equation represents the following set, which is a set of all points, also known as ordered triples, in r cubed whose y-coordinate is 3. This means that this equation contains all points whose coordinate is x3z. So we first draw the curve for the equation y equals 3 in the xy plane, as follows. This curve is analogous to the curve in r squared, but now we're graphing it in r cubed. This line represents all the points whose coordinate is x30. But remember that the equation y equals 3 does not contain any of the other two variables, x or z. This means that these variables are free to take any values. As a consequence, the following points are also part of the set of the equation y equals 3 in r cubed. These points represent the various values which include the z-coordinate. So all these points are also points that are generated by the equation y equals 3. Once again, in theory, we have an infinite number of points, so we usually connect all these points with a surface. In this case, the equation is represented by a plane. It's essentially a sheet of paper that is parallel to the xz plane, and is also perpendicular to the y-axis. In the same way, the equation x equals 3 is represented in r cubed as follows. It's also a plane that is parallel to the yz plane and is perpendicular to the x-axis. Finally, the equation z equals 3 will be represented as follows. It's also a plane that is parallel to the xy plane and perpendicular to the z-axis. At this point, we have equations to describe the coordinate planes of a three-dimensional coordinate system. The xy plane can be represented by the equation z equals 0. The xz plane is represented by the equation y equals 0, and a yz plane is represented by the equation x equals 0. Alright. Another concept that requires an understanding of these coordinate planes is the idea of a projection of an object on one of these planes. Let's keep it simple and first talk about the projection of a point on the coordinate planes. Say we have a random point in space. Let's call it point P, whose coordinates is equal to x, y, and z. If I were to view this point from above and shine a light directly above this point, it will create a shadow that is located in the xy plane, directly below point P. The location of this shadow in the xy plane is called the projection of P on the xy plane. This point has the same x and y coordinates as point P, but has a z coordinate of 0. Remember, the equation of the xy plane is represented by the equation z equals 0. So any point on that plane will have a z coordinate of 0. So let's denote the projection of P on the xy plane as point Q. It will have coordinates equal to x, y, and 0. Now, if I were to look at point P from the first octant, facing towards the yz plane, and I shine a light at point P, it will cast a shadow directly across point P. This is the projection of P on the yz plane, and has the same y and z coordinates as point P, but has an x coordinate of 0. The equation of the yz plane is represented by the equation x equals 0. So every point on this plane has 0 as its x coordinate. Let's denote the projection of P on the yz plane as point R, and it will have coordinates equal to 0, y, and z. Lastly, if I were to look at point P from the first octant facing towards the xz plane, and I shine a light at point P, it will cast a shadow directly across point P. This is the projection of point P on the xz plane, and has the same x and z coordinates as point P, but has a y coordinate of 0. The equation of the xz plane is represented by the equation y equals 0. So every point on this plane has 0 as its y coordinate. Let's denote the projection of P on the xz plane as point S, and it will have coordinates equal to x, 0, and z. In a later topic, this concept of a projection is going to be useful as we tackle more challenging concepts in multivariable calculus. Alright, in the next video, we will continue representing basic equations in three-dimensional space. Three-dimensional coordinate systems, Level 3. In the previous video, we started to describe basic equations in R-cubed, specifically describing equations on a three-dimensional Cartesian coordinate system. In this video, we will continue describing basic equations in three-dimensional space. Let's start by graphing the equation y equals x in R squared. Since this graph will provide us with a starting point to successfully graph it in R cubed. For starters, this equation is represented by a line in R squared, and has the form y equals mx plus b, where the slope is equal to 1, and the y-intercept is equal to 0. So we typically graph these equations by first plotting the y-intercept. In this case, it's equal to 0. Then we use the slope, which in this case is equal to 1, to generate a second point. Recall that a slope of positive 1 means that we move in the positive y direction 1 unit, and move in the positive x direction 1 unit. Remember, the slope can be interpreted as a rise over the run. Once we have our 2 points, we go ahead and connect them, obtaining the following straight curve. Now, if we were to graph this equation in R cubed, we would obtain the same curve in the xy plane. This curve has a y-intercept of 0 and a slope of positive 1. But notice that the variable z is not mentioned in the equation, meaning we have not specified z in any way, so we must assume that z can take on any value. This means that any particular value of z will get a copy of this line. Both the positive values of z, such as z equals 1, z equals 2, z equals 3, and so on, and negative values of z, such as z equals -1, z equals -2, and z equals -3, and so on. In this sense, the graph represents a vertical plane that lies over the line given by the equation y equals x in the xy plane. Notice that we started by drawing the curve on the plane that contained the variables for which the equation was defined. In this case, the equation was defined by the variables x and y, so we first graphed it on the xy plane. Then we drew copies of this curve on both the positive and negative direction of the missing variable, which was not expressed in the equation. In this case, the variable that was not expressed was z. Remember, variables that are not explicitly expressed in the equation are assumed to attain any value unless mentioned otherwise. We will go over equations in which the variables are restricted in a later video. Alright, Let's spice things up a bit and graph the equation z equals negative 2y plus 1. Once again, this equation has the form y equals mx plus b, but instead we have the equation z equals my plus b, where z is a dependent variable and y is an independent variable. We essentially treat the equation just like we did in the previous example, but instead of graphing it in the xy plane, we are actually going to graph the curve on the yz plane, as follows. Here we have a two-dimensional representation of the yz plane. We're going to graph the curve in this plane and then translate it into r cubed. So let's go ahead and plot what used to be the y-intercept, which in this case is now the z-intercept, on the yz plane. So we plot the first points at z equals 1. Then we use the slope. In this case, it's negative 2, which can be interpreted as negative 2 over 1, or in this case, the rise over the run, and use it to generate a second point. So from the z-intercept, we go ahead and move 2 units down along the negative z-axis, and move 1 unit to the right along the positive y-axis. Then we connect the points with a curve, as follows. Alright, having graphed the equation in the yz plane, we are ready to translate it into the yz plane of a three-dimensional Cartesian coordinate system. It's the same idea, but now we need to be able to navigate along the yz plane of this three-dimensional coordinate system. The yz plane is located here, the positive y-axis is located here, and the positive z-axis is here. So we literally draw the same curve we just graphed in r squared onto the yz plane of r cubed, as follows. Next we notice that the variable x is not expressed in the equation, and there are also no restrictions. This means that x can take on any value. As a consequence, at any particular value of x, there will be a copy of this line, both on the positive values of x, such as x equals 1, x equals 2, and x equals 3, and so on, and the negative values of x, such as x equals negative 1, x equals negative 2, x equals negative 3, and so on. In this sense, the graph represents a plane that intercepts the z-axis at z equals 1, and has a negative slope. The plane is inclined with a slope of negative 2 over 1. Alright, let's try the next example. This one requires graphing an equation in the xz plane. Let's graph the equation 2z plus 1 equals 3x. Notice that this equation is not in slope-intercept form, so we first need to arrange the equation into the slope-intercept form of a line. Notice that all the concepts you learned in your previous math classes come back in some shape, way, or form. This will be true as we dive deeper into multivariable calculus. Okay, in order to write the equation in slope-intercept form, we first need to solve for the dependent variable. In this case, the dependent variable is z, and the independent variable is x. This is similar to the way we solve for y when dealing with an equation in the xy plane, back in your pre-calculus class. So we go ahead and subtract 1 from both sides. Then we divide both sides by 2. Doing that, we obtain the equation z equals 3/2 x minus 1/2. Let's go ahead and graph this equation directly into the three-dimensional coordinate system. We first need to graph the curve on the xz plane. So looking at the equation, we see that the z-intercept is negative 1/2. So we first plot this point as follows. Then we notice that the slope is positive 3/2. So we use this slope to generate an additional point. So starting from the z-intercept, we move 3 units towards the positive z-axis and 2 units towards the positive x-axis. Then we go ahead and create a curve connecting both points as follows. Having created our first curve, we go ahead and make copies of this curve at positive values of y and at negative values of y. Remember, when a variable is not expressed in an equation and no restrictions are mentioned, the variable is free to take on any value. Lastly, we connect all the curves together and obtain the following plane that has a z-intercept of negative 1/2 and is also inclined with a slope of positive 3/2. Alright, these 3 examples were designed to illustrate the fact that you can use all your knowledge and experience from graphing equations in a 2-dimensional coordinate system and translate them into 3 dimensions. It might take you some time to get used to, but like in all your math classes, practice is key in developing this skill. In a later video, we will actually develop a more powerful way of describing planes in 3D space. For now, these examples were designed so you can start obtaining an idea of how to navigate through this 3-dimensional coordinate system. Alright, Let's try graphing something other than planes. Let's give it a shot and graph the following equation. X squared plus y squared equals 4. Notice that the variables that are explicitly expressed are the variables x and y. So we are going to first graph this equation in r squared, specifically on the xy plane. Recall from your studies of pre-calculus that this equation represents a circle centered at the origin with radius 2. So its graph is represented in r squared as follows. Now, if we want to graph this equation in r cubed, we go ahead and graph this curve on the xy plane as follows. Next, we notice that the variable z is not expressed in the equation. Remember, this means that every single value of z, both positive and negative, will have copies of this curve, which has the shape of a circle. Finally, we connect the curves with rulings as follows. This equation represents a cylinder centered in the z-axis. So in r squared, the equation represents a circle, and in r cubed, it represents a cylinder. Once again, this example illustrates the importance of specifying what coordinate system we are referring to, since it ultimately determines the graph of the equation. Alright, let's end the video by graphing one final equation. Let's graph the equation z equals x squared. Notice that the variables z and x are expressed in this equation. So we are going to go ahead and graph them on the xz plane. In addition, notice that this equation looks like the equation of a parabola, of the form y equals x squared. But in this case, the dependent variable is z, and the independent variable is x. Other than the variable z, this equation pretty much represents a parabola in the xz plane, and is graphed as follows. This is how this equation would look like in r squared. Next, we go ahead and graph this same curve on the xz plane of r cubed, as follows. Notice that the variable that is not expressed is y. This means that every single value of y will have a copy of this curve, since it's free to take any value of y. In addition, no restrictions have been imposed on the variable y. Next, we go ahead and connect the curves as follows. Doing that, we obtain the following surface. This surface is called a parabolic cylinder. We will study this surface and many more in a later video. For now, keep in mind that equations in r squared are usually represented by curves on a plane, and equations in r cubed are usually represented by a surface, but not always. They can also be represented by curves in space, as we will see in a later video. Alright, in our next video we will start exploring common formulas associated with a three-dimensional coordinate system. Three-dimensional coordinate systems, Level 4. Many of the formulas established for a two-dimensional coordinate system can be extended to 3 dimensions. It turns out that many of the formulas that you are used to working in r squared have natural extensions in r cubed. The first of these formulas is the all-familiar midpoint formula. Recall from your previous math classes that the midpoint of a line segment, denoted as P sub m, where m stands for midpoint, joining the points P1 with coordinates x1 and y1, and P2 with coordinates x2 and y2, has midpoint coordinates x sub m and y sub m equal to the coordinates x1 plus x2 divided by 2 and y1 plus y2 divided by 2, respectively. In the same manner, the midpoint of a line segment P sub m in space, joined by the points P1 with coordinates x1, y1, and z1, and P2 with coordinates x2, y2, and z2, has coordinates x sub m, y sub m, and z sub m equal to x sub 1 plus x sub 2 divided by 2, y sub 1 plus y sub 2 divided by 2, and z sub 1 plus z sub 2 divided by 2, respectively. Notice how we included a new variable. In this case, we included the variable z. For the most part, many of the equations that you were introduced in your previous math classes can be extended to 3 dimensions by just including this additional variable z. Let's go over an example. Find the midpoint of the line segment connecting the points 4, 3, 1 and negative 2, 5, 7. Let's go ahead and plot these points in a 3-dimensional Cartesian coordinate system, just so we can get a visual representation of where these points are located in space. The first point has coordinates 4, 3, 1, so we plot this point by starting at the origin and moving 4 units towards the positive x direction. Then we move 3 units towards the positive y direction. And lastly, move 1 unit towards the positive z direction. In the same manner, the second point is plotted by starting at the origin and moving 2 units towards the negative x direction. Then moving 5 units towards the positive y direction. And lastly, 7 units towards the positive z direction. This problem is asking us to find the coordinates of the midpoint of a line segment connecting these 2 points. So if you imagine a line connecting these 2 points in space, we are trying to find the point that is exactly halfway between these 2 endpoints, hence the midpoint. Also, keep in mind that geometrically, the midpoint divides a line into 2 equal parts. Finding the midpoint is easy, but really understanding what a midpoint represents from a geometric point of view is much more powerful and useful. When it comes down to it, the coordinates of the midpoints of a line segment is nothing more than the averages, or the arithmetic mean of the coordinates of the endpoints. So the average of the x coordinates is equal to 4 minus 2 divided by 2, which is equal to 1. The average of the y coordinates is equal to 5 plus 3 divided by 2, which is equal to 4. And the average of the z coordinates is equal to 7 plus 1 divided by 2, which is equal to 4. So the coordinates of the midpoint is equal to 1, 4, 4. Alright, let's move along to the next formula. Recall that in order to find the distance between 2 points, P1 with coordinates x1 and y1, and P2 with coordinates x2 and y2, in other words, the line segment from P1 to P2 in 2 dimensions, we use the distance formula, which was derived by using the Pythagorean theorem. In the same manner, the formula to find the distance of a line segment in space can be derived by using the Pythagorean theorem twice. Let's go over this simple exercise so we can work out our spatial visualization skills. Say we have 2 random points in space. Let's call them point 1 with coordinates x1, y1, and z1, and point 2 with coordinates x2, y2, and z2. In addition, let's create a box that includes points P1 and P2 as opposite vertices, where point 1 is located in the bottom corner of the box, and point 2 is located in the opposite top corner of the box. This way, both points have completely different x, y, and z coordinates, since these specific vertices don't share a common face on the box. If they did, then we would be working on a boring 2-dimensional problem, if both points were on the same face. Okay, in order to find the distance between point 1 and point 2, which is represented by the red line segment, we need to relate the length of this segment by using the coordinates of point 1 and point 2. Notice that we can actually find the coordinates of the other vertices by using the coordinates of P1 and P2. For example, I'm going to label the vertex directly across P1 towards the positive x-axis as vertex A, and label the vertex below point 2 as vertex B. Now, in order to assign coordinates to these vertices, in terms of the coordinates of P1 and P2, we notice the following. The front face of the box contains point 2. This face is parallel to the YZ plane. This means that every single vertex in this plane has x2 as their x-coordinate, including vertex A and B. Similarly, the faces on the sides of the box are parallel to the XZ plane, and contains point 1 in the left face and point 2 in the right face. This means that every single vertex on the left face will have the same y-coordinate as point 1, in this case y sub 1. So vertex A will have y sub 1 as its y-coordinate, and every single vertex in the right face will have the same y-coordinate as point 2, in this case y sub 2. So vertex B will have y sub 2 as its y-coordinate. And lastly, the plane that is located in the bottom of the box is parallel to the xy plane. This means that every vertex in this plane has the same z-coordinate as point 1. In this case, both vertex A and B will have z sub 1 as their z-coordinate. Now, in order to find the distance between point 1 and point 2, represented by the red line, I need to somehow relate this distance by using the coordinates of point 1 and point 2. It turns out that we can relate them by using right triangles. Notice that we can form a couple of right triangles in this box. The first right triangle contains the line segment formed by vertex B and point 2. in the line segment formed by vertex B and point 1. These two segments represent the legs of this right triangle, with the right angle being formed with the bottom plane of the box in the line segment formed by point B and point 2. In addition, the line segment formed by point 1 and point 2 represents the hypotenuse of the right triangle. In order to find the distance, we need to know the length of each leg. We can easily find the length of the leg formed by point 2 and vertex B. This is just going to be equal to the absolute difference between the points' z coordinates. Remember, we need the length to be a positive value, so we take the absolute value of the difference of their coordinates. The distance of the other leg is not as straightforward, and is a little bit more involved. I'm going to color this line segment with the color blue. It turns out that this line segment is also the hypotenuse of another right triangle. This right triangle has as its legs the line segment formed by point 1 and vertex A, and the line segment formed by vertex A and vertex B, with the right angle being formed by these two legs. In order to find the length of the blue line segment, which represents the hypotenuse of the second right triangle, we need to find the length of each of its legs. Once again, we can easily find these. The length of the segment formed by point 1 and vertex A will be equal to the absolute difference between the points' x coordinates, and the length of the segment formed by vertex A and vertex B will be equal to the absolute difference of the points' y coordinates. So now, we essentially have to apply the Pythagorean theorem to find the length of the blue line. The relations are as follows. The length of the blue line segment squared has to equal to the length of the line segment between point 1 and A squared plus the length of the line segment between point A and B squared. We know the length of the line segment between point 1 and A. It is equal to the absolute difference of their x coordinates. And we also know the length of the line segment between point A and B. It is equal to the absolute difference between their y coordinates. Simplifying the expression, we have the following. Now, let's apply the Pythagorean theorem to the other right triangle that has as its hypotenuse the red line, which is ultimately what we are trying to solve for. So we have that the length of the red line segment squared has to equal to the length of the line segment between point 1 and point B squared plus the length of the line segment between point 2 and B squared. From the first application of the Pythagorean theorem, we found the line segment between point 1 and B. This was equal to the following expression. And the length between point 2 and point B is equal to the absolute difference of their z coordinates. Combining them together and simplifying, we obtain the following expression. And finally, it's just a matter of taking the square root of both sides. Doing that, we obtain the distance formula in 3 dimensions between the points P1 with coordinates x1, y1, and z1, and point 2 with coordinates x2, y2, and z2. Notice that the equation resembles that of its 2-dimensional counterpart. The only difference is that we included an extra variable, in this case, z, because of the fact that we are dealing with a 3-dimensional coordinate system. Alright, in our next video, we will go over examples where we make use of this new formula, and we will also derive the equation of a sphere. 3-dimensional coordinate systems, Level 5. In the last video, we started introducing common formulas associated with a 3-dimensional Cartesian coordinate system, specifically the midpoint and distance formula. We will continue covering the distance formula by going over a couple of examples. Let's try the first example. Find the distance between the points 431 and -257. Notice that these are the same points from the midpoint example from the previous video. Let's go ahead and use the same graph that we used from that video. The first point will be located here, and the second point will be located here. This time around, the problem is asking for the distance between these two endpoints. In other words, the length of the line segment connecting these 2 points. It's just a matter of using the distance formula. A word of caution. The common mistake that many students make is not being consistent with the coordinates of each point. Notice that it's up to you which point you decide to designate as point 1 and which one you designate as point 2. As long as you're consistent, everything will work out. I'm going to designate the point with coordinates 431 as point 1 and designate the point with coordinates -2, 5, 7 as point 2. This means that the coordinates 4, 3, and 1 are going to represent x1, y1, and z1 respectively. In the same manner, the coordinates -2, 5, and 7 are going to represent x2, y2, and z2 respectively. So I'm going to subtract the x coordinates of the points from each other and square them. I will do the same for the y and z coordinates. Notice that we need to make sure we subtract the correct coordinates from each other. In this case, we need to subtract the x coordinates, y coordinates, and z coordinates from each other. Where you start getting into trouble is when you start switching the coordinates and start subtracting the wrong coordinate pairs. For example, you might end up subtracting an x coordinate with a y coordinate, or an x coordinate with a z coordinate. The best way to avoid this mistake is by appropriately labeling the coordinates given, so you can keep track which numbers represent the specific coordinates you're looking for. By subtracting the coordinates of the second point with that of the first point, we obtain the following. Then we square each result and obtain the following. Then we go ahead and add them. Lastly, we take the result and take the square root. We can simplify the radical expression by breaking it into a product of a square number and a factor of 76. In this case, 4 times 19. Doing that, and simplifying the expression, we obtain the distance between point 1 and point 2, which ends up being equal to 2 square root 19. Alright, let's try the next example. Determine whether the points P, Q, and R lie on a straight line. In other words, are they collinear? How can we determine if these 3 points lie in the same straight line? There's actually a couple of ways. Consider the following. Say we have 3 random points. Let's call them point A, point B, and point C. Let's also assume for now that they are collinear, meaning they lie on the same straight line. If this was the case, then it can easily be seen that the distance between point A and point C has to equal to the sum of the distance between AB and BC. From elementary geometry, the sum of the length of the 2 smaller line segments has to equal to the length of the line segment that includes these 2 smaller line segments. Alternatively, we can also use the following idea. If 3 points are not collinear, then they form a triangle. If this is the case, then by using the properties of triangles established in elementary geometry, we can show that the sum of the 2 sides must be greater than the third side. In other words, if these 3 points are not collinear, then they form a triangle. And we would have to show that the sum of 2 line segments has to be greater than the third side of the triangle. In other words, we need to show that line segment AB plus line segment BC is greater than line segment AC, and that line segment BC plus line segment AC is also greater than line segment AB. And finally, line segment AB plus line segment AC is greater than line segment BC. In either case, we need to find the length formed by each point and use one of these geometric relations to verify that they are collinear. Let's use the first geometric relation, since it's a lot easier to work with. Let's first find the length of each line segment. The line segment formed by point P and Q is found by subtracting the coordinates from each point and then squaring them. Doing that, we obtain the following. Then we continue simplifying the expression and obtain the following radical expression. We can further simplify this expression by breaking 18 into a product of a square number and another factor of 18. In this case, 9 times 2. Then we go ahead and simplify the expression, obtaining 3 root 2. Next, we find the length of the line segment QR. Once again, we use the distance formula and substitute the coordinates of each point. Doing that, we obtain the following expression. Then we go ahead and square the terms and simplify. Doing that, we obtain the following. We can simplify the radical expression by breaking it into a product of a square number and a factor of 72. In this case, 36 times 2. Then we go ahead and simplify the expression, obtaining 6 root 2. Finally, we go ahead and find the length of line segment PR. So we use the distance formula and substitute the coordinates of each point. Doing that, we obtain the following expression. Then we go ahead and square the terms and simplify. Doing that, we obtain the following. We can simplify the radical expression by breaking it into the product of a square number and a factor of 162. In this case, 81 times 2. Then we go ahead and simplify the expression, obtaining 9 root 2. Having found the length of each line segment, let's create a diagram to aid us in determining if these points are collinear. We know from the distances we found that points P and R form the endpoints of the longest line segments. This means that point Q has to be between these 2 points. Now let's go ahead and determine if the sum of the 2 smaller line segments add up to the line segment that includes these 2 smaller line segments. In other words, we're determining if the length of line segment PQ plus the length of line segment QR is equal to the length of line segment PR. Let's go ahead and substitute the values for each line segment. Doing that, we have the following. Next, let's simplify the left side of the equation. Notice how the left side is equal to the right side of the equation, meaning it checks out. Since this relation turned out to be true, we conclude that these points are indeed collinear. They lie in the same straight line. If we decided to use the second geometric relation, specifically proving that the line segments form a triangle, we would have to show that the sum of 2 line segments has to be greater than the third side of the triangle for all the following cases. The length of the line segment PQ plus QR has to be greater than line segment PR. The length of line segment PR plus PQ has to be greater than line segment QR. And the length of line segment QR plus PR has to be greater than line segment PQ. Let's go ahead and substitute the value of the lengths for each line segment into the relations. Doing that, we obtain the following. Next, we go ahead and simplify the left side of each inequality. Notice that the first inequality is false, the second inequality is true, and the third inequality is true. We're testing to see if these points form a triangle. We need all 3 inequalities to be true, but since the first inequality is false, we conclude that they do not form a triangle, meaning they must lie in the same straight line. They are indeed collinear. Alright, let's move along and continue exploring equations in 3-dimensional space. In the first videos, we introduced the basic equations of coordinate planes. Now we will explore the 3-dimensional version of a circle. Recall that the equation of a circle in R squared with center HK and radius R is defined to be the set of all points xy such that the distance between xy and HK is equal to the radius R. The distance between point P and point C has to equal R. Mathematically, we can express this as follows. The distance between the center, C, and a point on the circle, P, is equal to R. The distance between P and C can be found by using the distance formula in 2 dimensions. So we substitute the distance PC with the following expression. The square root of the quantity x minus h squared plus the quantity y minus k squared equals R. We can make the equation more user-friendly by squaring both sides of the equation. Doing that, we obtain the final equation of a circle with center HK. The quantity x minus h squared plus the quantity y minus k squared equals R squared. Keep in mind that this equation represents a circle in 2-dimensional space. We can form a surface using this curve by rotating it about its axis of symmetry. Doing that, we see that we end up forming a sphere in 3-dimensional space. Analogous to the definition of a circle, a sphere with center HKL and radius R is defined to be the set of all points xyz such that the distance between xyz and center HKL is equal to the radius R. Mathematically, we can express this as follows. The distance between P and C can be found by using the distance formula for 3-dimensional space. We substitute the expression for the distance of the line segment PC with the following. The square root of the quantity x minus h squared plus the quantity y minus k squared plus the quantity z minus l squared equals R. We can make the equation more user-friendly by squaring both sides of the equation. Doing that, we obtain the final equation of a sphere with center HKL. The quantity x minus h squared plus the quantity y minus k squared plus the quantity z minus l squared equals R squared. Once again, notice how this equation is extremely similar to that of its 2-dimensional counterpart. The only difference being that we included an extra variable. In this case, we included the variable z. Alright, in our next video, we will go over slightly more challenging examples that require the use of the distance formula. 3-dimensional coordinate systems, level 6. In this video, we're going to go over 3 slightly more complicated problems that require the use of the distance formula in 3 dimensions. Let's try the first example. Find the lengths of the sides of the triangle PQR with the given vertices, and determine whether the triangle is a right triangle, an isosceles triangle, equilateral triangle, or neither. How do we determine what type of triangle these 3 points form? Well, it depends. Say we have triangle ABC. If this triangle was an equilateral triangle, then the length of each of its sides would be the same, meaning that the length of line segment AB is equal to line segment AC, which is also equal to line segment BC. If the triangle were to be an isosceles triangle, then 2 of its sides would have to be the same, meaning that the length of line segment AB equals line segment AC, or line segment AB equals line segment BC, or line segment AC equals line segment BC. If the triangle were to be a right triangle, then we can use the converse of the Pythagorean theorem. Let's assume that in this diagram, line segment BC is a hypotenuse, meaning it's the longest side of the triangle. If the sum of the squares of the other 2 line segments, in this case AB and AC, are equal to the square of line segment BC, then the triangle is a right triangle. In any case, we need to find the lengths of each line segment. So let's go ahead and use the distance formula to find the length of each of the 3 line segments. The length of line segment PR can be found by using the coordinates of point P and R as follows. We go ahead and square the difference and simplify it by adding the sum. Doing that, we obtain the square root of 14. Notice that we cannot simplify this radical since the factors of 14 are 7 and 2. None of these are a square number. In the same manner, we find the length of line segment QR by using the coordinates of point Q and R as follows. We go ahead and square the difference and simplify it by adding the sum. Doing that, we obtain the square root of 45. We can simplify this radical by breaking apart 45 into a product of a square number and one of its factors, in this case, 9 times 5. Simplifying the expression, we obtain 3 root 5. Finally, we find the length of line segment PQ by using the coordinates of point P and Q as follows. We go ahead and square the difference and simplify it by adding the sum. Doing that, we obtain the square root of 59. We cannot simplify the expression because 59 is a prime number, so we leave the expression as it is. Having found the length of all the line segments of triangle PQR, we go ahead and start comparing the sides to determine what type of triangle the points form. Let's check to see if it's an equilateral triangle, meaning is the length of all 3 sides equal? In this case, no. Every single line segment has a different length, so we can eliminate this triangle from being an equilateral triangle or isosceles triangle. Let's test to see if it's a right triangle. We first need to identify the hypotenuse and the legs of the triangle. Remember, the hypotenuse is always the longest side of a right triangle. In this case, line segment PQ is a hypotenuse, and line segment QR and PR are the legs. Next, let's verify that the Pythagorean theorem is true, meaning that the length of line segment PQ squared is equal to the length of line segment QR squared plus the length of line segment PR squared. So we go ahead and substitute the values of each line segment into the equation. Next, we go ahead and square the values. Simplifying this expression and adding the values on the right side of the equation, we obtain 59 is equal to 59. So it checks out. Hence, by the converse of the Pythagorean theorem, triangle PQR is a right triangle, with the right angle located at vertex R. Alright, let's try the second example. If line L passes through the point A with coordinates 1, 2, 3, and is perpendicular to the xy plane, what are the coordinates of the points that lie on line L that are at a distance of 7 from point B with coordinates 3, -1, and 5? Alright, let's first draw a diagram so we have an idea of what we're dealing with. Let's first plot point A with coordinates 1, 2, and 3. Now, the problem states that line L passes through point A. In addition, we also know that this line is perpendicular to the xy plane, meaning it forms a right angle with this plane, as follows. This is a visual representation of line L that is perpendicular to the xy plane and passes through point A. The problem is asking us to find the points that lie on this line L that are at a distance of 7 from point B with coordinates 3, -1, and 5. So essentially, we're looking for all the points that lie on this line that are at a distance of 7 from point B. Since we are dealing with the distance between 2 points, it makes sense to use the distance formula in 3 dimensions. In order to use this formula, we need 2 points. Since we are trying to find the distance from point B to a point on the line, we will assign point B as point 1 and the point located on the line as point 2. Let's label this point as point P. Now, notice that we know the coordinates of point B. They are 3, -1, and 5. But how about the coordinates of point P? Well, let's take a closer look at the diagram. We know that line L passes through the points 1, 2, 3, and that it's also perpendicular to the xy plane. This means that any point on this line will have its x and y coordinates fixed. They will not change. So every point that lies in this line will be guaranteed to have an x coordinate of 1 and a y coordinate of 2. So point P should have 1 and 2 as its x coordinate and y coordinate respectively. In addition, since this line is perpendicular to the xy plane, the z coordinates of every single point that lie in this line will be distinct, since the points are free to move along this line in both the positive z direction and negative z direction. Since the values of z can change, we will assign the variable z as the z coordinate for point P. Now that we have values for the coordinates of point P, let's go ahead and apply the distance formula. Substituting the coordinates for point P and B, we have the following. We also know the distance from point B to point P has to equal 7, so we set this expression equal to 7. Notice that this problem reduces to finding the value of the z coordinates of point P. So let's go ahead and solve for z. First, we simplify the difference of the x and y coordinates. Then we go ahead and square them, and collect like terms, leaving the quantity z minus 5 squared intact. Next, we go ahead and square both sides of the equation, as follows. Doing that, we obtain the following expression. Next, we subtract 13 from both sides. Then we go ahead and take the square root of both sides. Here we have to be careful. Recall that when you take the square root of a quantity squared, this expression reduces to the absolute value of the quantity. Alternatively, we can take the square root of both sides, with the square root of 36 being equal to positive and negative 6. In either case, we have two distinct equations for which we need to solve for z. So solving for z on both equations, we obtain z equals 11 and z equals -1. Notice that we obtain two answers. This means that there are actually two distinct points that lie on line L for which they are at a distance of 7 from point B. The first of these is the point with coordinates 1, 2, 11, and the second point has coordinates 1, 2, and -1. Alright, let's try the final example. Find the point on the y-axis equidistant from the points 2, 5, -3, and -3, 6, 1. Alright, let's go ahead and plot the first point and label it as point A. Let's also plot the second point and label it as point B. This time around, the question is asking us to find the point that lies on the y-axis that is equidistant to these 2 points. Let's label this point as point P. Mathematically, we're trying to find the point for which the distance between point P and A is equal to the distance between point P and B. We can find the distance between each points by using the distance formula in 3 dimensions. But first, we need the coordinates of point P. From the problem, we know that point P lies on the y-axis. This means that the x and z coordinate remain constant. Specifically, both the x and z coordinates are equal to 0, leaving the y coordinate of point P free to change. So we will assign this coordinate with the variable y. Now that we have the coordinates of point P, let's go ahead and apply the distance formula to both line segments. The distance from point P to point A is represented as follows. And the distance from point P to point B is represented as follows. Next, we go ahead and simplify both sides by squaring the difference of the x and z coordinates, leaving the difference of the y coordinates intact for now. Next, we go ahead and square both sides to eliminate the square root from both sides. Then we go ahead and simplify the expressions. Now let's go ahead and expand the binomial from each side of the equation. Doing that, we have the following. We can eliminate the y squared term by subtracting it from both sides. Next, it's just a matter of solving for y by collecting like terms and isolating the variable. Doing that, we have that y is equal to 4. So the point that is equidistant to both point A and point B that lies on the y-axis is a point with coordinates 0, 4, 0. Alright, In our next video, we will start solving basic problems that require the use of the equation of a sphere. Three-dimensional coordinate systems, Level 7. In the previous video, we derived the equation of a sphere by using the definition of a sphere and the distance formula in 3 dimensions. Now we're going to go over 3 basic examples that require the use of this equation. Let's go over an example where the radius and center of the sphere are provided to us. Find the equation of the sphere with radius 5 and center 2, -1, 3. This problem is pretty straightforward. All we need to do is to use the equation of a sphere and identify the values for h, k, l, and r. Recall that the constants h, k, and l represent the coordinates of the center of the sphere. Notice that in this problem, the center is given to us. The coordinates of the center of the sphere are 2, -1, 3. So we go ahead and substitute these values into the equation as follows. Be careful with the value of k, since it's equal to a negative number. It will end up being a positive number when we substitute it into the equation. For the most part, the values of h, k, and l usually have the opposite sign than the one that is expressed in the actual equation of the sphere. Having substituted the values for h, k, and l, we go ahead and find the measurement of the radius. Notice that this value is also given to us. The radius is just equal to 5. So substituting this value into the equation, we obtain 5 squared, which is equal to 25. A common mistake that students make is forgetting to square the value of the radius, and just make it equal to 5, without squaring the expression. Make sure you square the expression since it's actually r squared, and not just r. So the final equation of the sphere is equal to the quantity x minus 2 squared plus the quantity y plus 1 squared plus the quantity z minus 3 squared equals 25. The graph of the equation is represented as follows. It's literally a sphere centered at 2, -1, 3 with radius equal to 5. Alright, let's try a more challenging problem. Let's go over a problem where the center and a point on the sphere are provided to us. Find an equation of the sphere that passes through the point 4, 3, -1 and has center 3, 8, 1. This problem is similar to the previous example. All we need to do is to find the center and radius of the sphere, and substitute the values for h, k, l, and the radius into the equation. The center is already provided to us, so the values of h, k, and l are 3, 8, and 1 respectively. Now, the only difference is that the radius is not directly provided to us. We actually have to figure it out from the given information. Notice that we are given the center and a point that passes through the surface of the sphere. Remember that the radius of the sphere is the line segment from the center to any point on the surface of the sphere. We know the center, and we also have a point on the surface. This means that we can use the distance formula to find the radius formed by these 2 points. So using the coordinates 4, 3, -1 as point 1 and the coordinates 3, 8, 1 as point 2, we go ahead and find the difference of each point's coordinates and square them. Doing that, we have the following. Next, we go ahead and simplify the expression, obtaining the square root of 30. Having found the value for the radius, we go ahead and substitute it into the equation. Then it's just a matter of squaring it. Doing that, we obtain the final equation of the sphere equal to the quantity x minus 3 squared plus the quantity y minus 8 squared plus the quantity z minus 1 squared equals 30. Alright, now let's try an example where the endpoints of the diameter are provided to us. Find an equation of the sphere with points 7, -1, -2, and 3, 4, 6 as the endpoints of a diameter. This problem is similar to the last 2 examples. In order to generate the equation of a sphere, we need the center and radius of the sphere. The only problem is that we are not directly provided with the center or radius. We actually need to find them. Let's find the center of the sphere first. Notice that we are provided with the endpoints of the diameter. Recall from elementary geometry that the diameter is a line segment that passes through the center of the circle. In this case, the line segment passes through the center of the sphere. So how can we find the coordinates of the center of the diameter? We can find the coordinates of the center by finding the midpoint of the diameter. In other words, we use the midpoint formula in 3 dimensions. So we essentially find the average of the 2 points x, y, and z coordinates. Simplifying the numerical expression, we have that the center of the sphere has coordinates 5, 3/2, and 2. Having found the center of the sphere, we now have the values for h, k, and l. All we have to do is to find the measurement of the radius of the sphere. We can find the radius in a couple of ways. We can find the distance from the center of the sphere to any of the endpoints of the diameter, either p or q, since a line segment from the center to any of these points represents the radius. Alternatively, we can find the distance from point P and Q. This would give us the length of the diameter of the sphere. Recall from elementary geometry that the diameter is equal to twice the radius. So finding the length from point P to point Q, we would actually find twice the length of the radius. Let's go ahead and find this measurement by using the distance formula in 3 dimensions, using point P as point 1 and point Q as point 2. We go ahead and find the difference of each of the points, x, y, and z coordinates, and square them. Doing that, we obtain the following. Next, we go ahead and simplify the expression, obtaining the square root of 105. Next is just a matter of solving for the radius. Remember, the distance we just found is the length of the diameter of the sphere, which is equal to twice the radius. Dividing both sides by 2, we have that the radius is equal to the square root of 105 over 2. Having found the radius, we go ahead and substitute this value into the equation of the sphere. Remember, we need to square the radius. Recall that the way we square a fraction is by squaring the numerator and denominator, as follows. Doing that, we obtain the final equation of the sphere, equal to the quantity x minus 5 squared plus the quantity y minus 3 halves squared plus the quantity z minus 2 squared equals 105 over 4. Alright, in our next video, we will continue going over examples that require the use of the equation of a sphere. 3-dimensional coordinate systems, Level 8. In the previous video, we started going over basic examples that require the use of the equation of a sphere. Now we will continue going over slightly more challenging examples. Let's go over an example where the equation of the sphere is not written in standard form. Show that the equation represents a sphere and find its center and radius. This problem is similar to the problems that you encountered in your pre-calculus class, especially when you were learning about conic sections. Because of the fact that these equations contain a quadratic term, also known as a power function of degree 2, we need to complete the square in order to obtain the binomial squared characteristic of an equation of a sphere. The first step in completing the square is to collect like terms and move the constants to one side of the equation, with the rest of the terms on the other side of the equation. For this problem, this has been taken care for us. Next, we want to group together the terms that contain the same variable. In this case, we group together x squared and 4x. Notice that y squared is the only term that does not have a corresponding linear term, so there's no need to complete the square on this variable. For the last variable, we go ahead and group together z squared and negative 8z. Next, we need to make sure that each of the quadratic terms has a coefficient of 1. Looking at the quadratic term, we see that all 3 of them have a coefficient of 1, so there's no need to factor anything out. Next, we go ahead and take the coefficient of the linear term from each group and divide it by 2, and square it, making sure we add the result to each respective group and on the other side of the equation. Doing that, we obtain the following. The purpose of completing the square is to obtain a perfect square trinomial and factor it as a binomial squared. In this case, each perfect square trinomial factors into the following binomials. Notice that the term that is added or subtracted in the binomial is actually the square root of the constant term we added. We also keep the sign of the linear term. Finally, we simplify the right side of the equation, obtaining the standard equation of a sphere, which is equal to the quantity x plus 2 squared plus y squared plus the quantity z minus 4 squared equals 25. The center of the sphere has coordinates equal to h, k, and l. In this case, the center has coordinates negative 2, 0, and 4. Remember that the value of h, k, and l have opposite signs than the ones expressed in the equation. Notice that y squared does not have a k term. This means that the value of k is 0. Many students forget this. If there's no term being added or subtracted, this means that the value for that coordinate is 0. Here, we also have to be careful with the radius. The number expressed in the equation is r squared. So to find the value of r, we need to take the square root of this expression. So the square root of 25 is 5. The radius of this sphere is actually 5, not 25. Alright, let's try the next example. Show that the equation represents a sphere and find its center and radius. Alright, similar to the previous example, let's go ahead and move all the terms with variables on one side, leaving the constant on the other side of the equation. So we subtract 8x, add 24z, and subtract 2y from both sides of the equation. Doing that, we obtain the following expression. Next, we go ahead and group the terms with the same variables. Doing that, we have the following. Next, we need the coefficient of the quadratic term to be equal to 1. So we go ahead and factor out 2 from each grouping. Alternatively, since each grouping has a factor of 2, we can go ahead and divide every single grouping, including the constant, by 2, as follows. Next is just a matter of completing the square for each variable. So we go ahead and take the coefficient of each of the variables' linear term and divide it by 2, and squaring the result, making sure we add this value to both sides of the equation. One term is added to its respective grouping, and the other is added to the constant on the right side of the equation. Next, we go ahead and factor each of the perfect squared trinomials into a binomial squared. We also need to simplify the constants on the right side of the equation. Doing that, we obtain the following equation of a sphere. The quantity x minus 2 squared plus the quantity y minus 1/2 squared plus the quantity z plus 6 squared equals 163 over 4. Looking at the equation, we see that the coordinates of the center is equal to 2, 1/2, and -6. And the radius is equal to the square root of 163 over 2. Remember, to obtain the radius, we need to take the square root of the number expressed in the equation, since it actually represents r squared, not r. Alright, let's go over the final example. Find equations of the spheres with center 2, -3, 6 that touch the xy plane, the yz plane, and the xz plane. In this problem, we are asked to find the equation of the sphere with center 2, -3, and 6 that touches each of the coordinate planes. We already have the center of the sphere. All that is left to find is the radius of the sphere. This means that we need an additional point, so we can use the distance formula in 3 dimensions. The second point we need is that point where the sphere touches each of the coordinate planes. In essence, the point where the sphere touches the coordinate plane is called the tangent point. In this case, the coordinate planes would be the tangent planes to this sphere. Let's first find the tangent point that is formed with the xy plane. Here we have the center. Let's label it as point C. We want to find a point on the xy plane that is tangent to a sphere with a given center. Let's label this point as point T. Recall from elementary geometry that a line tangent to a point on a circle is perpendicular to the radius at that point of tangency. In the same manner, a plane that is tangent to a sphere is perpendicular to the radius of the sphere at that point of tangency. This means that we can draw a line segment from the point of tangency on the xy plane to the center of the sphere. And this line segment is essentially the radius of the sphere. Notice that the point of tangency is actually the projection of point C onto the xy plane. Recall from the previous videos that the point projected onto the plane has the same x and y coordinate of the point being projected. In this case, point T has the same x and y coordinates as point C. In addition, since this point is located on the xy plane, its z coordinate is equal to 0. Now that we have the coordinate of point T and C, let's use the distance formula to find the radius. Using point T as point 1 and the center as point 2, we go ahead and find the difference of each of the point's coordinates. Doing that and squaring the expression, we obtain the following. Then we go ahead and simplify the expression, obtaining the square root of 36, which is equal to 6. So the equation of the sphere with center 2, -3, 6 that touches the xy plane is equal to the quantity x minus 2 squared plus the quantity y plus 3 squared plus the quantity z minus 6 squared equals 36. Notice that since both points T and C share the same x and y coordinates, their difference reduced to 0, and the distance was solely equal to the difference of the point's z coordinates. So all we had to do is count how many units from the center we need to move to reach the xy plane in a z direction. This works because the coordinate planes are perpendicular to one of the coordinate axes. the radius of the sphere touches the plane in the direction of a single axis, as opposed to two or more axes. In the same manner, the equation of a sphere with the same center that touches the YZ plane can be found in the same way. Since the plane is perpendicular to the radius of the sphere, all we have to do is count how many units from the center do we need to move to reach the YZ plane. In this case, we need to move 2 units in the positive x direction. Notice that this is the same as the x coordinate of the center. But keep in mind that this will not always be the case. We're trying to find the distance from the center to the YZ plane. Since the x coordinate of any point on this plane is 0, we are actually finding the distance from 2 to 0, which is just equal to 2. So the equation that touches this plane is the quantity x minus 2 squared plus the quantity y plus 3 squared plus the quantity z minus 6 squared equals 4. Finally, the equation of a sphere that touches the xz plane can be found by counting the distance from the center to the xz plane, since it's also perpendicular to the radius of the sphere. In this case, we need to count the distance along the y-axis, which is just equal to 3. So the equation of the sphere would be equal to the quantity x minus 2 squared plus the quantity y plus 3 squared plus the quantity z minus 6 squared equals 9. Keep in mind that all we had to do is to count the distance from the plane to the center of the sphere. In these examples, because the planes were perpendicular to one of the coordinate axes, the problem reduces to just counting the distance from the center to the coordinate plane along a single axis. If the plane were to be slanted or tilted, then we would be moving along 2 or more axes. We will go over these types of examples in a much later video. Alright, in our next video, we will go ahead and cover 2 final examples that require the use of the equation of a sphere. 3-dimensional coordinate systems, level 9. In the previous video, we covered intermediate level examples that required the use of the equation of a sphere. Now we are going to go over 2 more challenging examples. Let's go over the first example. Find an equation of the largest sphere with center 5, 4, 9 that is contained in the first octant. This example builds upon the problems from the previous video. The problem is asking us to find the largest sphere with center 5, 4, 9 that is contained in the first octant. How can we figure this one out? Let's first think about an easier problem that is related to this one. Say we have a random circle that is placed in the first quadrant of a 2-dimensional coordinate system. If we were trying to find the largest circle that is contained in this quadrant, one way we can solve this problem is by expanding the circle until it literally hits one of the 2 axes. If we allow this to happen, the circle will actually be tangent to one of the coordinate axes. It turns out that we will actually hit the coordinate axis that is closest to the center. In the 3-dimensional case, if we allow this sphere to expand, as if we were inflating a ball or a balloon, it will end up hitting one of the coordinate planes. Similar to the 2-dimensional case, the sphere will end up touching the coordinate plane that is closest to its center. Let's actually find the distance from the center of the sphere to each of the 3 coordinate planes. Recall from the previous video that since all 3 coordinate planes are perpendicular to one of the coordinate axes, finding the length reduces to just measuring the distance from the center to each of the coordinate planes, along the direction of a single coordinate axis. This means that the xy plane is 9 units away from the center. The yz plane is 5 units away from the center, and the xz plane is 4 units away from the center. If we were to let the sphere expand, it will end up hitting the xz coordinate plane. If the sphere is allowed to expand beyond this plane, it will cease to be contained in the first octant. So the radius of the sphere is equal to 4. The largest sphere that is contained in the first octant with the given center is represented by the equation the quantity x minus 5 squared plus the quantity y minus 4 squared plus the quantity z minus 9 squared equals 16. The hard part of this problem was to understand the idea of containing the sphere in the first octant. It turns out that the shortest distance from the center to the coordinate plane limits how much the sphere will be able to expand and at the same time be constrained in the first octant. Alright, let's try the next example. Find an equation of the sphere with center in the xz plane and passing through the points P, Q, and R. Notice that in this problem, we are not provided with the center or the radius of the sphere, nor are we provided with the endpoints of the diameter. We are dealing with a completely different problem, not addressed in the previous videos. We are asked to find the equation of a sphere with its center located in the xz plane. All we know from this specific information is that the center of the sphere will have coordinates equal to h, 0, and L. Since we don't know what the x and z coordinates of the center are equal to, we leave them as h and L. In addition, we also know that k is equal to 0 because any point located in the xz plane has 0 as its y-coordinate. Next, we are given 3 distinct points that are located on the surface of the sphere. We need to somehow use these points to find the value for h, L, and the radius of the sphere. How do we accomplish this? What kind of geometric relations can we construct with the given information? We have an expression for the center of the sphere, and we also have 3 points that are located on the surface of the sphere. With this information, we can generate a relation for the radius of the sphere by using the center and one of these points. It turns out that we can actually generate 3 relations that represent the radius of the sphere. It can be seen that the radius is equal to the length between point P and C, which is also equal to the length between point Q and C, which in turn is also equal to the length between point R and C. Since all of these relations represent the radius of the sphere, we can equate all 3 expressions together. This is similar to the law of sines that you learn in your pre-calculus or math analysis class. Recall that you can equate any 2 relations with each other in order to solve a specific expression. By using the distance formula in 3 dimensions and using point P as point 1 and the center C as point 2, we obtain the following expression for the radius. In the same manner, we can find an expression for the distance between point Q and point C as follows. Simplifying the expression, we obtain the following. And finally, the distance between point R and the center C is expressed as follows. Simplifying the expression, we obtain the following. Since all of these expressions represent the radius of the sphere, we can equate all 3 expressions with each other. We can make the expression more user-friendly by getting rid of the radical, so we go ahead and square all 3 expressions as follows. Next is just a matter of solving the system of equations. We need to solve for 2 distinct variables, in this case h and L. We can also generate 3 equations from the given relations. This is more than enough to solve the system of equations. Let's start by equating the first expression with the third expression. Let's avoid using the second expression for now, since it contains 2 binomials squared. We want to work with the simpler expression first. Notice that when we equate the first and third expression, we can eliminate the h squared term, since it appears on both sides of the equation. Next, let's go ahead and expand the binomial squared. Doing that, we have the following. Notice how we can also eliminate the L squared term, since it appears on both sides of the equation. Next, we go ahead and add like terms, moving the constant on one side of the equation, and the terms with the variables on the other side. Doing that, we have the following. Finally, we go ahead and solve for L. Doing that, we obtain L equals 12. Now we need to equate 2 distinct expressions and substitute this value for L and solve for h. Let's equate the first and second equations together. Next, let's go ahead and replace the value for L with 12 and simplify the expressions. After that, let's go ahead and expand the binomial square. Notice that the h squared terms cancel out, since it appears on both sides. Then it's just a matter of getting all the terms with the variables to one side and the constants to the other side, and simplify the expression. Lastly, we go ahead and solve for h. Doing that, we obtain h is equal to -7. We now have the center of our sphere. To find the radius is just a matter of substituting the values for h and L into any of the 3 line segments, since all 3 of them represent the radius of the sphere. Let's go ahead and substitute them into the expression representing line segment PC. Simplifying the expression, we obtain the square root of 257. So the equation of the sphere that is located in the xz plane and that passes through the points P, Q, and R is represented by the equation the quantity x plus 7 squared plus y squared plus the quantity z minus 12 squared equals 257. Alright, in our final video on three-dimensional coordinate systems, we will go over how to graph equations whose domain are restricted to a given interval. Three-dimensional coordinate systems, level 10. In this final video on three-dimensional coordinate systems, we'll go ahead and learn how to graph equations and inequalities that are restricted to a given interval. Recall from your prior math classes that the graph of a function can be restricted to certain values of its domain and range by specifying the restriction using inequalities. For example, if we were to graph the equation y equals x squared and r squared, it will look like this. It's essentially a parabola that attains a minimum value at x equals 0. Now, say that I only want to graph this equation starting at x equals 1 to positive infinity, as follows. The way we mathematically express this graph is by denoting an inequality that describes this restriction. In this case, we want to graph the equation y equals x squared when x is greater than or equal to 1. If we don't want to include the value at x equals 1, then we write x is greater than 1. Then, the closed circle is changed to an open circle to let us know that we do not include the value at x equals 1. In the same manner, we can restrict the graph of an equation in three-dimensional space. Let's go over the first example. Describe the region of r cubed represented by the equation y equals 0 when z is greater than or equal to 0. Recall from the previous videos that the equation y equals 0 represents the xz coordinate plane and is graphically represented as follows. Next, we go ahead and apply the restriction. In this case, we only want that part of the graph where the values of z are greater than or equal to 0. This means that we only want that part of the graph that is located on the regions where the value of z are positive. In this case, everything above the xy plane. So our graph will look like this. Notice that there was no restrictions on the values of x. Remember, this means that the values of x are free to attain any value. If on the other hand, we add an additional restriction, like x is greater than or equal to 0, then we will need to erase that part of the graph, y equals 0, with the values of x are negative, as follows. Because we only want that portion of the graph where the values of z and x are positive. And this is the region that is graphed. It's essentially the first quadrant of the xz coordinate plane, if we were to look at it from this direction. Alright, let's try the next example. Describe the region of r cubed represented by the equation x squared plus y squared equals 4 when z is between -2 and 2 inclusive. When dealing with these types of problems, it's always a good idea to ignore the restrictions for now and graph the equation as if there was no restrictions. Recall that this equation represents a cylinder in r cubed. The variables expressed in the equation are x and y, so the expression x squared plus y squared equals 4 represents a circle in the xy plane. In addition, since we are graphing this equation without any restrictions, we create a copy of this circle on every single value of z, as follows. So technically, this cylinder extends all the way to positive infinity in the positive z direction, and negative infinity in the negative z direction. Next, let's go ahead and apply the restrictions. Notice that the inequality describes an interval, in this case, the acceptable values of z that this equation can attain, or the values between -2 and +2 inclusive. This means that our cylinder will only have copies of the circular trace between these values of z, as follows. So we now have a cylinder that has a height of 4 units. What if we wanted to graph only the left half of the cylinder? What restriction would we have to add? In this case, we only want that part of the graph where the values of y are negative. So we need to add the following inequality. Y is less than or equal to 0. If I want the right half of the cylinder, then I include the inequality y is greater than or equal to 0. Notice that in both cases, we are including 0. If you don't want to include 0, then we remove the equal sign and add dashed lines on the sides of the cylinder, as follows. As you just saw, we can control what portion of the graph we want to focus on by restricting certain values with inequalities. Alright, the next type of graphs we will focus on are the graphs of inequalities themselves. recall from your previous math classes that when you graph an inequality in R squared, we are trying to find a specific region whose points satisfy the inequality. For example, say we want to graph the inequality y is greater than or equal to x squared. The first step is to graph the inequality as if it were a regular equation, as follows. Next, we need to determine the region above or below the graph that satisfies the inequality. In this case, we want to shade the region where the values of y are greater than the values of x squared. This means that we need to shade the region above the graph, as follows. Recall that this region determines a set of points that satisfies the inequality. So if you were to choose any point on this region, it should satisfy the inequality. In other words, you should obtain a true statement when you substitute the coordinates of any point located in this region into the expression. Notice that the set of points that will make this inequality a true statement also includes the points located on the parabola itself. If we were to change the inequality to y is greater than x squared, then we would graph the function using dashed lines. This means that we don't include the points located on the function itself. Now let's go ahead and graph some inequalities in R cubed. Describe the region in R cubed represented by the inequality x is greater than 3. Alright, the first step is to graph the inequality as if it were an equation. So we are essentially graphing the equation x equals 3. Recall that this equation represents a plane that is parallel to the yz coordinate plane and located 3 units in the positive x direction. Next, we go ahead and apply the inequality. In this case, the values of x have to be greater than 3. This region consists of all the points in front of the plane x equals 3, not including those points on the plane. Alright, let's try the next example. Describe the region of R cubed represented by the inequality. Here we have an inequality that represents an interval. The way we deal with these types of inequalities is by graphing the function in the middle of the inequality by equating it with the left value and the right value. So we first want to graph z equals 0 and z equals 6. These equations represent planes that are parallel to the xy plane. So we go ahead and graph them. Next, we apply the inequality. So the region represented by the inequality are all the points between these two planes, including the points on the bottom plane, but not including the points located on the top plane. Alright, let's try the next example. Describe the region of R cubed represented by the inequality x squared plus z squared is less than or equal to 9. As always, let's go ahead and graph the inequality as if it were an equation. This equation represents a cylinder with circular traces of radius 3, located in the xz plane, and centered in the y-axis. Next, let's apply the inequality. We want to shade that part of R cubed where x squared plus z squared is less than or equal to 9. Another way of representing this inequality is by taking the square root of both sides, as follows. So we essentially want the set of all points whose distance from the y-axis is at most 3. These points are located inside of the cylinder. We also want to include those points that are located on the cylinder. Alright, let's go ahead and try the next example. Describe the region of R cubed represented by the inequality. Alright, once again, we have an inequality defined by a given region. In this case, the middle function represents a sphere, and the numerical values represent the smallest and largest value of the radius that the sphere can attain. So let's go ahead and graph the equation x squared plus y squared plus z squared equals 1, and the equation x squared plus y squared plus z squared equals 4. We essentially have 2 concentric spheres centered on the origin. Next, let's go ahead and apply the inequality. Let's rewrite the inequality by taking the square root throughout, as follows. So we want the set of all points that are at least 1 and at most 2 from the origin. In other words, we want to shade the region that is between these 2 spheres, including the points that are located on the surface of the sphere with a radius of 2 and a sphere with a radius of 1. Alright, say that we only want the upper half of these spheres. In other words, all the points that are above the xy plane. How can we accomplish this? We can denote these points by including an additional inequality. In this case, we want all the points that are above the xy plane, or all the points that contain a positive z coordinate. So we go ahead and include the inequality z is greater than or equal to 0. so we can restrict the values of z to take on positive values only. Doing that, we would obtain the following graph. Alright, let's go over the final example. Write an inequality to describe the region. The region inside a cube centered in the origin with side length equal to 4. In this problem, we are asked to come up with the inequalities that describe the given region. We basically want the set of all points that are located inside a cube of side length equal to 4. We can start by generating each of the faces of the cube, since each face represents a plane. The top and bottom face can be obtained by graphing the equation z equals 2 and z equals negative 2, as follows. In addition, since we want all the points that are between these two planes, we want to set up an inequality that represents the region between these two planes. We express this region as follows. Next, we want an expression that defines the sides of the cube. The sides that are parallel to the xz plane are represented by the equation y equals negative 2 and y equals 2, respectively. And the inequality that defines the region between the planes is expressed as follows. And finally, the front and back faces of the cube are parallel to the yz plane and can be obtained by graphing the equation x equals 2 and x equals negative 2, respectively. And the region between these two planes can be expressed as follows. So the inequalities that define the set of all points inside a cube centered on the origin with side length equal to 4 are defined by these three inequalities. Alright, now that we have laid the foundations in navigating and maneuvering a three-dimensional coordinate system, we are ready to learn about vectors, which will provide us with the tools necessary to tackle on the rest of Calculus 3.